So this talk will be about deriving an Erlang interpreter from the mechanized formal semantics of Core Erlang, and so this talk so this paper is also one of the latest papers from this high assurance refactoring project, and I've mentioned with formal semantics that if you have a formal definition for a programming language, you can build formally verified tools on it, or you can prove properties of programs. And the last talk was about proving properties of programs, but this talk will be more about deriving formal tools from the semantics. And the main topic here is a formally based interpreter, so deriving that from the semantics itself. So I've mentioned before that the semantics formalizes Core Erlang because it has fewer language constructs than Erlang, and because it's also an intermediate language for other languages in the Bean family, like Elixir. And I've also talked about the syntax in my last talk, but so repeating it a bit. So a Core Erlang expression can either be a value or a non-value. Values are things like integers, atoms, or lists, and non-values are expressions like function calls or function applications. So in the last talk, I only really got into the sequential layer of the semantics. However, there are these two upper layers here, and these are the layers that formalize the Erlang actor model. So, but a bit of we should look back in the sequential layer again. So as a reminder, in the sequential layer, reductions are made on these configurations. So we have a frame stack and the regex, and the regex is the thing we are evaluating right now, and the frame stack is the continuation for the evaluation. And I brought you some more reduction rules from this layer. And these are how to evaluate the try expression. So if we have a try expression in the regex, what we need to do first is put it on top of the frame stack and then evaluate the expression in the head of the try expression. And that expression can either evaluate the sequence of values or an exception. And this is a sequence of values because of multiple bindings here, but if this expression evaluates to a sequence of values, what we need to do is go on with the E2 branch because we didn't have any exceptions, and these values that were calculated will So these bindings here, so these are the values for the bindings here, and these values will need to be substituted into that expression, and through this substitution operation. So basically, these variables will get syntactically replaced by these values. And what happens if that expression gets evaluated to an exception is we need to go to the catch side, and in the catch side there is also some substitutions going on because Erlang expressions have Erlang exceptions have 3 components to them, and these components need to be substituted in to these bindings. And the last rule here with the exceptions is how to propagate an exception. So I've mentioned that the frame stack the continuation for the evaluation. And what happens if we don't have a try block on top of the frame stack? Well, we need to propagate that this exception until we either catch the exception in a try block, or we run out of the frame stack and terminate the program. And give back the exception at the end of the evaluation. So this was the sequential layer, and I want to talk about the Erlang actor model a bit as a refresher. So in the Erlang actor model, processes are called actors, and they communicate through passing messages, and these messages arrive at the mailbox of the other of the process that it was sent to, and that other process can deal with these messages when it wants to and how it wants to. And processes can also spawn other processes, and also processes can be linked together. And what a link means is that when one of these processes terminates, all of its links will be informed of this termination, and they can deal with this exit signal that was sent out in the appropriate way that needs to be done. So the Erlang actor model can be formalized using two layers. And so the middle layer that builds on top of this sequential layer is called the process local layer. And this layer will do reductions on processes. And the upper layer will be called the interprocess layer. And that will do the orchestration of everything. So all the processes inside the Erlang node. But for the process local layer, I said that we will be doing reductions on processes. And processes can either be living or dead. And the living process is basically a frame stack, or Redux, that we have already seen before. And they also have a mailbox and a set of linked PIDs, and also this trap exit flag. And processes can also be dead. So after they terminated, these are notated with T, and T is just a map between the linked PIDs and the exit signals to be sent out. And in this layer, reductions are made during actions. And the actions can be a few different things. So an action can be tau, which is a silent reduction step. You will see in a moment what that means. And actions can be send or arrive, and these control the signal sending and signal arrival. An action can also be spawned, and this is what does process spawning. And it can also be self, and self just gives back the PID of the process. And by the way, on these slides, everywhere you see an iota is a process identifier, so a PID. And here is so here is an example of a reduction in this process local layer. So we have a process here, and this needs to be reduced using this action. So this is basically sending out an exit signal, but from a living process. So by manually calling Erlang exit. So as you can see, this frame is on the frame stack. The value to be sent out with this exit signal is V, and if we do this sending action, then this is what needs to be done to this process. And remember that this process local layer is only concerned with this process itself. So the other process that will receive this exit signal, but that will come along later in the final layer of the semantics. But sending this exit signal, so what sending this exit signal means to this process is just that the top frame be taken off the frame stack, and we need to give the value true as the value, as an LX. And this is another reduction in this process local layer. So you might have been wondering what a tau action was. And the tau action is basically the action that connects this process local layer with the bottom sequential layer. So to do a tau action on a process just means that we need to do one of these sequential, one of these reductions in the sequential layer. So getting from one configuration to the other, and so in the process local layer, you can see the new frame stack and the regex here. So unlike the sequential layer, which is deterministic, this process local layer is actually non-deterministic, and that is for a couple of reasons. One of them is arrival actions. So at any point in time, a signal might arrive to a process, but actually, if we don't count arrival actions, then a living process will know how to go on with the evaluation. So that would be deterministic. But since arrivals can happen anytime, this makes reductions on living processes non-deterministic. And actually, reductions on dead processes are also non-deterministic. So a dead process can only do one thing, and it's sending out exit signals to all of its links. And we know that there should be an order for this, but this order is actually never specified anywhere. So that is why this is another point of non-determinism. So that process can send out exit signals whichever order it wants to. And the final layer is the interprocess layer, and this does reductions on node configurations, and these node configurations are a bit different than nodes in Erlang, because so we have a process pool, which is a map between process identifiers and the processes that are identified by them. But a node configuration also has an ether, and that is where signals, and that is where signals float around after they've been sent out, but before they've arrived to their destination, and this ether needed to be formalized because of this signal ordering guarantee. There is actually only one thing that we need that we know about signal orders, and is that sending a signal between a source and the destination, or actually I should say that sending multiple signals between the source and the destination, so the order of those signals, so the order those signals will arrive will be the same order that they have been sent out. But otherwise, the order of signals arriving is actually also non-deterministic. And so I said that you can think of this interprocess layer as a layer that orchestrates that orchestrates all of these reductions. So here you can see one of these reduction rules, and all of these will be pretty similar. So what you have on top is a reduction in the layer below. So that is actually in the process local layer. And what this reduction is if we did a reduction on a process in the process local layer, and the action was a sending action, here is what we need to do in terms of the whole system. So you had the ether before. That signal that was sent out needs to be put in the ether. And as for the process pool, the process associated with IOTS, it used to be P, but we made a reduction on it. So now the process associated with IOTS is now P prime. And as you can see, for this bottom part, the interprocess layer, alongside the action, we also need to give the PID of the process that the action was done on. And this is another rule for the interprocess layer, and this one is much simpler. So here is what the tau action means in terms of the whole system. So if we do a local step on a process, then the ether is unmodified. But the process pool is modified. Before we had this process P, but now iota is paired with this process P prime. So this interprocess layer is also non-deterministic, and it's not just non-deterministic because of the process local layer below it. It's also non-deterministic because every reduction step we need to choose which process to do the reductions on. So as I mentioned before, everything you see here was also implemented in the ROC proof assistant, formerly known as COC, so these three layers of the semantics were defined using inductive definitions. And for this paper, what we wanted to achieve was deriving an interpreter from these rules. And actually, so deriving this interpreter is actually pretty straightforward, but there are a few steps that need to be taken along the way. So these inductive definitions are not inherently executable in ROC. So the first thing that needed to be done was to make three functions that work equivalently to these inductive definitions, and so these functions would need to be computable, and this way you can do these reductions automatically. And as you can see, so these functions need to be equivalent, and that equivalence actually needs to be proven. So as for the sequential step function, if you remember, there were four rules for those trie expressions, and here they are actually in the code. And yeah, the formalization it's kind of unreadable here, but you need to focus on basically to minimize the number of branchings here in ROC. We match on the regex first, and then if we need to, we match on the frame stack. And if we need to match on anything else, then we match on those after. And but you can see here with, for example, strie, that all this rule needs is a trie expression to be in the regex. So that is why we are not matching on K here. But for the others, we do need to match on K. The process local step function was a bit interesting to define. But one thing that I want to point out is the arrival of exit signals, and these are the rules in the semantics, and as you can see, there are a lot of preconditions for them. So to make this into a function, a lot of nested pattern matches were needed, and figuring out a good order for that was a bit of a challenge. And And as for the interprocess step function, so in this function, the first thing to match on is this pool lookup, and that is equivalent to this. And this is because for this function, a node needs to be given along with an action and the PID of the process that we want to do that action on. And we need to look up the PID in the process pool, because we need to actually see if that process is in the process pool. But otherwise, when we do that, we can just proceed with the actions accordingly. So that's great. Now we have a function that works equivalently to the interprocess layer, and we can do steps using it. However, for an interpreter, it is actually it is actually not very convenient to use this. And that is because this action parameter needs to be provided every time. And it's not really an interpreter's job to construct these actions every time. So we decided to make this interfacing function that we call the node simple step function. And for this function, we need to give a node, and whereas for the previous function, we needed a PID and an action. This function needs either a PID or a pair of PIDs. So I've mentioned that with living processes, the actions other than arrival are deterministic. So if we give this function a PID, then we do a non-arrival action on that process associated with the PID. But if we give this function a pair of PIDs, then if there is a signal floating in the ether between these two PIDs, then the function will make that signal arrive to the destination. And so the interpreter itself cannot be completely constructed in ROC, and that is because, as I mentioned at the end of the previous talk, you cannot have infinite recursion in ROC, because it would lead to logical inconsistencies. But there is a way in ROC to extract these definitions into other languages, like Haskell, OCaml, and Scheme. And for this project, we chose Haskell. So we need to extract this node simple step function into Haskell, and for that, and actually is using the default extraction works great, but during the extraction process, a number of optimizations can be done on the way, and that is because ROC gives us ROC gives us some optimization options. So these are things like replacing ROC data types with Haskell data types, or ROC functions with Haskell functions. And also we can inline functions. And the three major optimizations that we pointed out in the paper were as follows: making substitution strict. So if you remember those try rules, so when variable bindings were calculated, so after variable bindings get calculated, they need to be replaced in the program. Yeah. So the variables need to be substituted. That's not how I should say it. So the calculated value needs to be put in to the place of the variable that was calculated. And to do that in the semantics, we just go through the whole structure of the program and replace all these variables when they need to be done. However, since Haskell evaluates expressions lazily, this didn't really happen, and there was a pretty nasty space leak issue with this. So that is why these substitution functions need to be made strict. The other optimization here is replacing the extracted map and set operations with the Haskell variants because they were just more efficient. And the last thing to talk about here is simplified substitutions. So the substitutions were defined very generally, and a lot of meta theory was developed along the way. However, for this specific use case for Erlang, substitutions can be simplified a bit. So that was the third optimization step. So after we've extracted this function and optimized along this extraction, we also need a scheduler component, and that is because so now we can do reduction steps on a node, but we still need to pick which process to do these reduction steps on, and that is the scheduler's job. The scheduler picks one of the processes from the process pool to do these reductions on. And one other thing that was defined is what we've called the interpretation cycles, and that goes something like this. So when the scheduler chooses a process to be in focus, that process in focus makes at most k non-reliable steps, and then if the process terminates, so if a process terminates during this k non-arrival steps, then all of its links will get notified immediately. And the third thing in this cycle is all signals floating in ether will get delivered. But otherwise, the scheduler is free to choose which process to make the non-arrival steps on. And actually, just defining just defining this scheduler and the interpretation cycles. So just by defining these two things, we eliminate all points of non-determinism in the system. So every time we run this interpreter, we can get the same result. So yeah, and the last thing needed here is for a way to integrate all of this into the Erlang ecosystem, and for that we needed a so-called pretty printing component because the semantics is for core Erlang after all. So we piggyback on the Erlang compilers compilation between Erlang and Core Erlang, because that is actually pretty well founded. So we convert our Erlang code into the abstract syntax tree in Core, and then we extract that definition of the program in Rock. And now we can use the program in the interpreter. And so another tool that was built in this paper was a so-called computation graph explorer. And the idea came from this figure, which was in one of the previous papers in the project. And so basically, as I said, there is a lot of non-determinism involved during the evaluation of these node configurations, and what this figure shows is this program called PMap, which is basically a parallel execution of maps. It just splits a list in two, and then does a map operation on both halves of the list, and then concatenates them together. But doing this concurrently leads to many different interleavings that are possible. And this figure was made manually by hand. However, since we now have a way to do these reduction steps automatically, we can make a component that makes figures like this. And actually, so this is basically the same figure as this one, just some nodes are more compressed here. And here, every one of these nodes is one of those node configurations. So with the process pool and the ether. And you can see that many different execution paths could be taken. And you can also see that this is not a tree; it's a proper directed graph. So some paths can lead to the same node configurations. And as I said, this figure can now be built automatically. So for closing, here are some pros and cons for deriving an Erlang interpreter from formal semantics. One of the pros is the interpreter can be made with little effort. So as you saw, there were many steps involved, but they were actually pretty straightforward. And the interpreter is formal based, which cannot be said of most tools made these days. And it can also serve as a reference interpreter for other interpreters and compilers. And reference is a keyword here, because as you might imagine, building an interpreter like this will not lead to very efficient calculations. And that is because of two things. One of them is that reduction steps are high level, which are inherently slower. So, I mean, compiling into Beam code and then just running that would be way faster because it is just lower level. But the other thing here is that that inefficiencies in the formalization can carry over to the interpreter as well. And to illustrate that, this is an insert so this is an insert from a performance data table in the paper. And this example is a concurrent program with 100 processes running, and the four rows are the four correspond to the optimization steps made during the extraction in ROC. And I don't really want to bore you with the details, but the thing here is even at our best version of this interpreter, where substitutions are made strict and map and sub operations are replaced, and we use the improved substitutions, up to 96% of the time is spent just substituting variables, because we need to go through the entire structure of the program. So a solution to that would be to redefine the semantics using variable environments instead of substitutions. And I would like to thank all of you for listening to me. And I would also like to thank Péter Bereczky for his work on the semantics, and Arsenii Fomin for that graph, that computation graph exploring tool. And also I'd like to thank EEF for their financial support in this paper, and finally the organizers of this workshop for enabling me to travel here to Singapore and present these two papers. That's about it. And I don't know if we have time for a question. I guess probably not.
No, I don't think. Like maybe while Max gets.
Yeah, sure.
You can take one.
So.
Thank you for the interesting talk.